All right, welcome back to the counting slide. So let's pick up where we left off. We were talking about these things called multisets, which are like sets, but you can actually have multiple elements. And when you have duplication, those elements are indistinguishable. They're the same thing, okay? And we were learning how to count how many ways we can permute all the elements of a multiset to select n objects from a set of m varieties, counting multisets. Okay, so it looks like this. You made a weird encoding with ones and zeros, the zeros marking like where the new bin happens that you're choosing the next variety out of. We talked about dogs. And so now I want to give you some practice with this and then also some other things that we learned last time. So two crushed ices for us right now. This first one is not about multisets. So what I'd like you to do is take a look at this one, try and figure out how many strings you can make, and the strings have the alphabet A, B, C, D, so those are the only characters you can use to make your string, and it needs to be of length 12, okay? How many strings of length 12 can you make over this alphabet that contain exactly 4 B characters, okay? So no more, no less, 4 B characters. So give that one a try, and we'll talk about it. There's a common error that might happen with this question, and that's why we're talking about it. Okay, so here's how you do it. You'll notice that you need to fill in 12 slots, right? 1, 2, 3 with a character, right? You're building up a size 12 string. You're trying to count all the different ways you can do it, all the way to a character 11 and character 12, right? You got to fill in with characters. What should these boxes be? The idea is you have 4 B's to choose from, so you need to pick which slot the B's will go into. How many different ways are there to put a B into this string? 4 of them. Okay, so that's 12, choose 4, remember. All the ways of choosing 4 B's and putting them somewhere in these in this size 12 string. And then, like maybe you pick this one, I don't know why I'm drawing capital B's. This one, and this one. Those are the B's, and then the rest have to hold other characters, right? So you might say, okay, there are 8 characters left, and they could either be any of these, right? So it's 4 to the 8. And this is where it's incorrect. It's not 4 here, because that 4 includes B's, okay? It's the size of the set including B's. So that might mean there are extra B's in the rest over here. That might mean you'll put some more B's over here. We don't like that. You can only choose for the rest of this string among the 3 other characters, A, C, and D. Do you see that? And you got to pick 8 of them. Okay? That's how it works. You can only choose A from A, C, and D after you've picked the spots for the 4 B's. Okay? That is the idea. So hopefully this makes some sense, and that one is the answer. It's 3 to the 8, times 3 to the 8, not times 4 to the 8. Okay, so that is that, and okay, let's move on to this one. This one's about multisets. Okay, so we've got a bunch of coins. There's just a giant pile of coins, and you got as many as you would like to grab out of each like stack, a little sub-stack of pennies, nickels, dimes, and quarters. So I guess the first question is, how many ways are there to select 25 coins, exactly 25 coins from the piles? Okay, try and figure that out. How many different ways are there to select 25 coins total from these piles? And so this is a job for our handy-dandy counting multisets formula, because we're trying to select 25 coins from a set of 4 different types of coins. Yeah? So it's really just this. We have n equals 25, m equals 4, and so we just plug in the formula. Whatever it is, it's n plus m minus 1 over m, choose m minus 1, sorry. Is that right? Yes. So that's the answer, and we can spell this out. It's 29, 28, oh, choose 3. Okay? We went through the hard part of figuring out how we're going to encode all this stuff. It's like, okay, I'm going to take 3 pennies, 4 nickels, 5 dimes, and then the rest are 4 3/4, right? And so you have 25 ones total, but this is our encoding, and the number of different ways you can write a string like that, which stands for how you can select these objects, is exactly this many. Okay, so we're just plugging in that formula there. So hopefully you got that one. And now the other one is slightly trickier. Okay, so how many ways are there to select 25 coins again if at least 5 of the chosen coins must be quarters? Yeah? So this one, you have to notice that this 5 is special. It's like you don't get to choose the same amount anymore, okay? So you have to pick the 5 quarters up front, okay? You're stuck with 5 quarters. And the key thing here is also that we're assuming that all the quarters are the same. That quarters, all coins, are the same type, denomination type, are indistinguishable. Very long word. Okay? And so this means that you picking those 5 quarters up front, just there's only one way to do that, because all the quarters are indistinguishable from one another. Okay? So you got to pick the 5 quarters. There's only one way to do that. It's just you go and grab 5 quarters. They're all indistinguishable, so it doesn't matter which actual quarters you take, like which dates they have on them. It's just a process of grabbing 5 quarters, which are all the same to us. Okay? So there's only one way to do that when they're indistinguishable, to pick 5 quarters. And then, how many coins do we have left to choose from? Okay? Times all the ways to select how many coins? 20 coins left, right? Ways to select 20 coins from the piles. Which this all becomes just this answer, which is then n is now 20, okay? So it's 20 plus, m is still 4, plus 4 minus 1, choose, still 4 different types of coins, right? Choose 4 minus 1. Okay? So that is apparently 23, choose 3. And that's how many different ways you can select those 25 coins when you've already made the decision that 5 of them have to be quarters. Okay? And so it is a bit weird to think about it this way, as your quarter choices being indistinguishable, but just understand that you've now made a choice. There's only one way to make that choice, and now there are fewer coins to choose from, to have to choose randomly. Okay? That's the idea. All right. So that is counting multisets. You're done with it now. Let's now talk about that sum rule again. At the very beginning we talked about this, and it's going to come back to haunt us. Okay? So the whole idea for the sum rule is when you have 2 sets, like S1 and S2, if they don't overlap, like here's the elements of S1, here's the elements of S2, if you want to get how big both of them together are, well, yeah, you just count how many are in S1 and count how many are in S2. But unfortunately, you've all seen Venn diagrams that look like this. What happens when they overlap? This is S1, this is S2. Oof. That means that you're going to double count when you try to add all the things in S1, the size of that, plus all the size of S2. You've counted this twice, haven't you? So the way that we get around this, the way that we mathematically say, okay, yeah, we know how to solve for the size of a set with that's not disjoint, it's union. So we call it the principle of inclusion-exclusion, because you got to like put some in, take some out. Put some in, take some out. That's how it works. Include and exclude. It's a weird little process. And so it's a way of counting the size of a union of any 2 sets, no matter if they share elements or not. This is the real answer. Okay? If you have 2 sets A and B, and they share some elements, like A has 4, 5, 6, B has 1, 2, 3, 4, 5 elements, then the size of both of them together is the size of A, which is the 6, plus the size of B, which is the 5, but really the total is 6, 7, 8, 9. Yeah? So we got to take away all the ones that are overlapped, because when we add the A, we add 2 from here, and when we added the B, we added 2 more from here, and so we counted that middle part twice. So let's just take it back away once. A intersect B. So you just take away that thing you double counted, and now you have the real size. Okay, that's A union B, and this generalizes to fancier sets, more than just to A union B union C. If you want to solve for the number of elements in those, it's A plus size of A plus size of B plus size of C, and then you subtract some of these intersections, and then you add back in an intersection of 3 sets. You subtract intersections of 2 sets and add in the intersection of 3 sets. It's very weird, and there is a pattern, but I'm going to let you read the book for that. Okay, that is something that I don't really want to cover. It's very fancy. You can prove it with induction, actually, but it's nothing we really have time for, unfortunately. So that is inclusion exclusion. I guess you can think of it as the generalized sum rule, maybe. So that's that. Now let's talk about algorithms. This is a computer science class, after all, kind of, right? So let's talk about how you can generate all the different permutations of some set, all the different combinations, all the different subsets of the elements of a certain set. Okay? To get there, we have to talk about lexicographic ordering, which is another very nice long word. It just means dictionary order. Okay, so all the words in a dictionary are ordered by definition in lexicographic order. Okay, and so the way that you actually compare strings in a programming language, it's based on this order as well, this dictionary order, with additions for like numbers and weird symbols and things. Okay, because you got to be able to say like, oh, the string with the percent sign is, yeah, that's less than the opening brace string. Okay, that's all. So yeah, so ABC, it comes before BCD in the dictionary, of course, so it's less. Okay, ABC is less than ABD because it comes before it in the dictionary, if this were to be a real word. That's all. That's all lexicographic order is. And so the way that I'm about to show you, the way that the book has of generating these permutations and combinations of a certain set, is we're going to generate them in lexicographic order because we know when we're done, because we get to the biggest element in the dictionary, right? The final element of the permutation. And this will actually be the topic of your next lab, if like nothing goes horribly wrong. Okay, so these two algorithms that I'm about to show you will be the topic of your next lab. So let's get started. It's really not bad. It's just parsing this function down here. It takes a while. It translates into a bit of code, and it's subtle. Okay, this is very easy to understand. Okay, this is the first outer function call that you make, and it's called gen lex permutations of n. Okay, and what it means is please generate all the permutations of the set 1, 2, 3, ... all the way to the number n. And you can of course use the permutations that you get back to index into like an array of n things. So it doesn't just have to give you back numbers, but this is how this function works. Okay, generate all the permutations of the numbers from 1 to n. Okay, and so the way it works is, okay, the first permutation is 1 through n in this order because this is lexicographic order. It's getting bigger, right? 1, then 2, then n, all the way that way. And then the final permutation that you could ever get to is this one. Okay, n minus 1, 2, and then 1. It's like this is A and this is Z. You can't get any bigger than this string. Okay, treat the permutation as a string. It's like this is the A, B, C, D, Z, all the way down that way, and this is the Z, Y, X, B, A. Yeah, you can't make a string of a certain length bigger than this one. Okay, and use all of those characters. You see that? So that is the idea. And so you're just going to output all of them. So here's the first permutation, output it. And then while you haven't gotten to this last one yet, well, you'll generate the next one using this fancy function, and then output it, okay? And so this will just continue to output permutations in lexicographic order, okay? So, for example, if n equals 5, we're going to go back to the function in a second. If n equals 5, the very first permutation is 1, 2, 3, 4, 5 in that order, okay? That is like everything's less than everything else. That is the first permutation in lexicographic order. You can't find one that is smaller, okay? That's the idea. And then it's the job of next perm to take the one you just had, like this one, and find the next one to go to, okay? So this one's weird. This one's weird to think about, so we're going to go through why it works, all right? So the first thing that it does is it finds the largest index such that pk, and here are the elements of the permutation, pk is less than pk plus 1. And it looks like it's looking at this one, okay? That's the largest index such that this one is smaller than this one, okay? You can't go to this one because there's nothing after it, right? So it's going to stop there. It's going to be like, okay, that's my k. And you're actually at the end if there is no such k. Oh, shoot, I'm so sorry. We're here. You're at the end if there's no such k because like all of these are greater than the next one, yeah? And so then you find the largest index such that pj is greater than pk, okay? So where is a number that is greater than pk, okay? Which index? It's this one. So this is your, let's see, pk and pj. Yeah, 4 and 5. Then, I keep going to that one, I'm sorry. You swap them, swap pj and pk, and then you reverse the order of everybody from k plus 1 to n, okay? So these get swapped, 1, 2, 3, 4, 5, and from this one, sorry, again I did it, and then from pk plus 1 onward, you reverse their order, okay? So this one's not going to really do anything because it's like, from this one onward, reverse it, and so it just stays 5, okay? And oops, it's 5, 4. They got swapped. And so this is the next one in the sequence. This is the next smallest, or the next biggest permutation. It's the second smallest one, okay? That's the idea, because it comes after because the 5 is bigger than the 4, and then there's really only one left that you can pick from here, okay? And that's the next one. So what it's going to do is it's going to go in this order, okay? And so what should be the next permutation after this? Maybe take a second to think about that. Well, you can keep 1 the same, 2 the same, 3. You can't really change this to be 6 or anything. So you're kind of stuck moving this 3 around. We're probably going to have to change it to 4, right? And then we have 3 and 5 to do something with. And because we want this to be as small as possible, 3 better come before 5, right? It's like A should come before B in the dictionary, because this one's the bigger one. This should be the next permutation. You see that? So let's figure out how in the world the algorithm's getting us to there, all right? So again, you're going to call next permutation on the one that came before it, and somehow it's going to spit out this thing, okay? What's it going to do? So find the largest k, find the largest index such that p of k is less than the one that's right after it. And it looks like this one is it, p of k, okay? It's less than 5. 5 is not less than 4. So this is p of k. And then, all right, where is p of j now? Let j be the largest index such that p of j is greater than p of k. Okay? Where is the largest index such that this one's bigger? Okay? Dun dun dun. It happens to be this one. This is the largest index. It's the rightmost one. So it can't get any bigger. And it's bigger than 3. 4 is bigger than 3. P of j. That's the idea. And then we're going to place it, okay? We're going to swap them. It goes through this like intermediate step. Maybe I'll write it in green. it's going to swap PK and PJ, right? It swaps them. Oops. And then it reverses the order of everything after. So it's going to be 1, 2, 4, 5, 3. And then it reverses everything from the one after PK, so this one, this index, onwards. So these two get reversed. So this then becomes this 1, 2, 4, 3, 5. You see that? Which is equal to that. That's how we do it. So it's just finding the next spot that it could increment and then making the smallest thing that it could put after it, okay? The smallest sub-permutation. And because it's going to be in decreasing order like this, that's when you know you're at the end of a certain run, you have to reverse it, so then it's smallest to largest again, okay? That is my hand-wavy way of analyzing this algorithm, and hopefully it's helping. Please yell at me if it's not good enough, and I'll explain it more. And so then you're just going to use this algorithm on and on and on forever, and it's really going to work. It's going to give you the next largest permutation, and it will stop at the largest one. And so then you're done. Okay, so that is something that you will be implementing in your lab. Think about how you might want to do it. All right, so that's permutations. Let's talk about how to generate all combinations. Okay, and then let's see what we got left. Yeah, this is going to work. So this is generating subsets. Okay, how do we generate subsets? So it's going to do this. Gen lex subsets. Again, it's going to work with numbers, but you can use those as like indices into a vector or something to get real elements. But what it's going to do is it's going to make all of it generates all the subsets of size R from the set that you can make out of the set 1, 2, 3 on all the way to n. Okay? So all the different subsets you can make of this out of this set of size R. Okay? That's what it's going to do. And so it's again going to output them in a certain order. So it's like you should save this as like an array or something so that it stays in order, but really is representing a set. Okay? So the first set is this. It's 1, 2, R minus 1, R. That's like the smallest thing. And then the biggest set that you can make is n minus R plus 1 all the way to n. Okay? So that is the idea. So let's give a concrete example again. Let's say that R is 3 and n is 5. The very first subset of size 3 out of the set from 1 to 5 is 1, 2, 3. Right? That's the first one. And then the last one, that is 3, 4, 5. Can't get any bigger than that one. Yeah? And that's the idea. So it goes and figures out, okay, what's the next one? What's the next largest subset after this? So that is the job of this scary looking function again. All right? So let's break it down. So it's going to go and find the largest index such that S of k is less than n minus r plus k. Now that is a lot. What does that mean? And the best way to explain it is through intuition again. Okay, so maybe let's make a smaller arrow so that I can show you exactly what's going on here. What's the next smallest subset? You got to make your elements out of this set, 1, 2, 3, 4, 5. What should be the next smallest one? What could you pick? And the answer is 1, 2, 4. You see that? That's the next smallest subset in that order. Even though order is not supposed to matter. It's doing it in a special way, so we have to remember this order. It's 1, 2, 4. What's the next one? 1, 2, 5, right? That's what the algorithm is doing deep down. That's what this function is doing. What's the next one? Well, 1, 2, 5, we're kind of like out of luck. We got to get bigger. It's like a number system, and like we have to add. Okay, so this is like 1, 3 now. What's the smallest number I could put here? Well, what about 1, 3, 4? Yeah, we've already considered like 1, 3, 2, right? Can't do that one. 1, 3, 3 doesn't make sense because it's a subset. It has to be 1, 3, 4. Okay, so that's what happens, and then it becomes 1, 3, 5, and this is all going to keep going. And I think like the next subset is going to be, okay, we've exhausted all of these. Let's do 1, 4, 5. And then we've gone through 1, 4, 5. We can't make this 5 because we can't have anything smaller than that. So now it's 2, 2, 3, 4. This is what the algorithm's going to do. Okay? And this is the ordering. I hope you can understand this ordering. It's like this is A, B, C. This is A, B, D. It's the next biggest one. Yeah? That's the idea. It's dictionary order still. So, how in the world is this algorithm doing that? So what it's doing is it's finding the largest index such that S of k is less than n minus r plus k. So let's try some examples to understand like what this even means, n minus r plus k. Well, all it's saying is, okay, we have 3 and 5 again. We have 5 minus 3 plus k, okay? So for example, this first element is S1. We want to see if S1 is less than n minus r plus 1, yeah? 5 minus 3 plus 1, which equals, and remember we're looking at this one, 5 minus 3 plus 1, which is 5, 4, 3, 2, and then 3. Yeah? And then we want to see if S2 is less than 5 minus 3 plus 2, which should be 4, right? S3 is less than 5 minus 3 plus 3, which is 5. And these numbers are the last elements in those respective positions that you could ever put there. Okay? This location can't get bigger than 4. That's what it's saying. This location can't get bigger than 5. That's what it's saying. This location can't get bigger than 3. It's looking for the first one it can change that still has places to go. This one can still get bigger. That's all it's doing. See that? This one's easier. So it's just like, okay, that one can get bigger. Let's make it bigger. That's all. And then, after that, because we just made it bigger, we're going to have to increment things, everything after it. So this is k plus 1 to r, so everything after, like we picked this one, there's nothing after it, so that doesn't really help here. But now it's like this one gets flipped, so everything after it needs to be increased, okay? Like here, this one got flipped, so everything after it needs to be increased, okay? And increase from a certain starting position then, though. It's got to be, where is it saying that? It equals the one that came before it plus 1. Okay, so it's just going in order now. That's all. So this becomes 2, and then 2 plus 1 is 3, 3 plus 1 is 4, and this one is like, okay, 3 plus 1 is 4. That's all it's doing. Okay, that's how it orders these things. So hopefully that's making some sense, and it's a bit intuitive. And so this is eventually going to get to the end, and we've made all our subsets, and we're sure that we're done. So it's quite nice, and a useful little algorithm to know. I have seen on the internet at least one interview question about this kind of process, this kind of algorithm, and so it's useful to know. Okay, so that is generating subsets algorithmically. You've done it. Now, 2 more main topics and we're out of here. Okay, so let's make sure you understand these algorithms first, though. Let's take this permutation 5, 4, 7, 6, 3, 2, 1 of this subset. What is the next largest permutation? And honestly, maybe next time this should go between these. Yeah. So what's the next largest permutation after this one? Well, it's got to be of 1, 2, 3, 4, 5, 6, 7. It looks all like this. What are we going to do? We have to, well, use this next perm. Okay? Find the next index that is smaller, the biggest index that's smaller. Dun dun dun. This one is still bigger. This one is the next one that's smaller. Okay? 4, then 7. It's smaller. The rest of these are bigger. See that? So this is the one that changes. This one's going to change. Are you ready? So it becomes what? We take, then we got to find the one to swap it with. What's the largest index such that pj is greater than pk? Okay? Just algorithmically, what are we doing? What's this one? 2, 1, j, oh, sorry. pj is greater than, I have to write it. pk, pj, which one's bigger than this? The biggest index. It looks like it's this one, because 6 is bigger than 4, and it's the biggest index. Okay, it's like this is 0, 1, 2, 3. That one's the biggest. This is pj, and so we'll swap them. 5, 6, 7, 4, 3, 2, 1. and then we swap everything after pk. Okay, reverse the order of pk plus 1 through to n. So this is pk plus 1 through to n. We swap them, reverse them all. So this is 5, 6, and then 1, 2, 3, 4, 7. So it's like using everybody but these two in that order. So that's the next smallest one, and this is the answer. Okay, so just follow the algorithm. It will make sense, and hopefully, eventually, you will be good enough to just write this. Just see this and notice, okay, yeah, it's the 4 that needs to change. That's how we do it. Okay, that's what you need to understand. Okay, so that is that, and now it's time for a different topic. Okay, which is still similar to combinational things. So it's called the binomial coefficients, which you have learned about already in like an Algebra 2 class. So here is my fun binomial made of variables named b and o, and so it expands to, if you just FOIL it a bunch of times, it's going to be this, bbb plus bbo plus bob plus boo plus all these other things all the way to oo. You can simplify it into this, right? Because the order doesn't matter. Like Bob and BBO, those are the same thing. It's B squared O. You got 3 of those, yeah? But this is interesting because the order doesn't matter here. Just due to math, the order didn't matter of these coefficients, or of these variables. We can break them up together. What can this tell us about subsets, generating combinations? These coefficients for the b squared o, the bo squared, and the o, they are special. They're called the binomial coefficients. For this one, they're 1, 3, 3, and 1, right? We've learned about these. And they're the same reverse. They're their own palindrome. And sorry, there was a typo. This fancy thing called the binomial theorem says that, okay, if you want to know, like, what is the coefficient out in front of b squared o, you just turn it into this. If you have a plus b to the n, you want to ask, okay, what's the coefficient out in front of a to the k to times b to the n minus k? It has to be this. They have to add to n, right? That's the idea, because it's to the nth power. It happens to be n choose k, which also happens to be the same as n to choose n minus k, and that's why like they can be reversed. That's why they're palindromes, because this is like the other side of this. Okay, you can like flip them across a mirror. It's beautiful. So that is the binomial theorem. Let's try and prove a few things. Okay, at least one thing at least. So this is quite interesting. Okay, this whole binomial coefficient thing. And it also gives rise to this other thing called the Pascal triangle, right? Pascal's triangle. So this was invented by Blaise Pascal. He noticed that you could make this fancy triangle, right? Of all the numbers of the form n choose k. You got your, in order, n is 1. Try all the numbers that you can make. N can be 0 or 1. And then n equals 2. N choose 2 choose 0, 2 choose 1, 2 choose 2. Can't get any bigger than that or smaller than that. Then n equals 3, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 2, and 3 choose 3. And the idea is, this is all, like, these are all come together. How many ways can you choose 0 things out of one thing? It's 1. How many ways can you choose 1 element out of a 1-element set? 1 way. How many ways can you choose 0 elements out of a 2-element set? It's 1s. 1s all along this line. And then the rest of these, what was the trick? They like add together, right? How many different ways can you choose 1 thing out of a 2-element set? So that's 2 ways, right? So these all get added together. And so here's our 1, 3, 3, 1, because you're adding 2s and 1s, okay? 3 choose 1 is 3. 3 choose 2 is also 3. Yeah? That's the beauty. And this is this fact that you can add these two together like this, and we're actually doing stuff with combinations, is called Pascal's identity, okay? The number of ways to select a set of k items from a set of n items, so that's this one, it's the same as the number of ways to select k minus 1 from n minus 1, plus the number of ways to select k from n minus 1, okay? So that is called an identity because we're showing that two things are equal, that they're identical, yeah? And so that's the diagram, and let's try and prove that identity. Why not? We've got to prove, here's our theorem, n choose k is equal to this plus this. Those two smaller things. Yeah? So, here's the secret. here's how the proof goes through. Pretend that we are counting all the different k subsets of a set A, because that's what we want. We want all the different k subsets out of a set with n elements, right? And so what we notice by the sum rule is that we can break down all these separate subsets of size k of A, because we can take all the subsets like that contain an and all the subsets that don't contain an. Okay, so like maybe it's like 1, 2, an, 5, this is 1, 3, an, all the different subsets that contain an. Of length k, subsets that contain an, so I guess this needs to be 4 if I'm doing it like that. And then this one is all the length k subsets that don't contain an. Hopefully it's obvious that these are disjoint. None of these subsets over here have an in them, so they can't be the same as any of these over here. 1, 5, 2, 7. These are disjoint from one another. They don't share any elements. And they sum together, they union together to be all of the different kinds of k subsets of this set A. Yeah? It's just the ones that contain a certain element and the ones that don't contain a certain element. They are together all of the different kinds of k subsets. Okay? Hopefully that makes sense. That's the key. Okay? Because then we just need to figure out, well, how many of these k subsets are there of A that contain A of n, and how many are there that don't contain A of n. Okay? So this one, it's this first thing. Now let me try and show you why. Well, if you want to find all the k subsets of A that contain an, you've already made a choice for an. So just pick for the rest of everybody then. You only need to pick up to n-1 elements, because you've saved the nth element. That's going to be A to the n. Okay, so that's how many you need to pick from. And how many things do you need to pick? One less, because you're still saving that one of those elements for A of n. n-1 choose k-1. And then this one's the other one. It's n-1 choose k. And why? Well, again, you have one less option, because you're making sure you're choosing from not all the entire set, but all the entire set excluding this particular element. So you have n-1 things to choose from again, but this time you're actually going to choose k things still, because you still haven't made a choice for everybody. Like these, you're saving room for an, but for this one, you're just ditching an and trying everybody else. Okay, so you still have k elements to pick. And so that's why the identity holds, and hopefully that that makes some sense. Please yell at me if it didn't, but that is the real proof. Okay, no induction, nothing fancy. It's just notice that this breaks down like this by the sum rule. Okay, which seems simple. A simple rule can prove some powerful things. So now it's your turn. So give this all a try, and then we have our last topic. Okay, so tell me, what is the coefficient of x to the 5, y to the 3rd in this particular binomial? Okay, 3 to the x minus 4y, and this is all to the 8th power. Okay, so what is that coefficient? And this is kind of messed up because you got some negatives, you got some 3's and some 4's. Okay, so normally, if this was just x plus y, you'd get something, but we have some extra things now, don't we? Okay, so the answer is what's out in front of, let's see, what is the first one? The x? We got x to the 5th. Okay, so what is the coefficient supposed to be? It is n choose k. So it's going to be n, which is the original thing, which was 8, I think, and then k, which is 5, I think. Yeah, 5, so 8 and 5. So it's 8 choose 5 out in front. Out in front of, let's see here, x5, y3. But because you took 5 x's, you're also taking 3 5 times. You see that? And because you're taking 3 y's, you're also taking negative 4 3 times. So that's the real coefficient. Yeah? That's the idea. It's a bit generalized, but hopefully that makes some sense. Okay, you just figure out how many x's you're taking, and this 3 had to come along for the ride, yeah? Because we took 5 x's, we're taking 5 3's too. And same for the -4 and the y. Okay, so that is the idea. So that's the coefficient for that one. And then let's do the coefficient of this one in this binomial. Okay, so again, we have x to the 6, y to the 1 out of 7 things. So the coefficient is going to be out in front of x6, y1. If we just do the formula, it's going to be something times this. It's going to be 7, choose, and it's the 6. It's the thing out in front of the x, right? 7, choose 6. And then, okay, we had 6 x's, which means that this -2 in front of the x came along 6 times as well. And then also we had 1y, which means that the -5 came along once. Okay, so that's the real coefficient. And so we're just plugging in the formula. Notice that this generalizes to when you have coefficients as well. Okay, that's all. And so really these are the coefficients, this and this, right here. Those are the real coefficients. That's the real answer. And, oops, I forgot the 3. We took the -4 3 times, excuse me. So that's that. That is the, those are the real 2 answers, I hope, this time. All right, so that is binomial stuff. We've proven a powerful identity. And then the final thing to talk about for this chapter is this thing called the Pigeonhole Principle, which has a fun little name, and it's fun to talk about too. So enjoy this meme. The idea of the Pigeonhole Principle is it's like the simplest thing in the world, but it actually turns out to be quite powerful, and we're going to prove some very weird things, I promise. So at least one weird thing. Here's the Pigeonhole Principle. If you have n+1 pigeons and n boxes, I don't know what you're doing with pigeons and boxes, but you're having some fun apparently. If you know, like here are 1, 2, 3, 4, 5, 6 boxes, and you have 7 pigeons, and you know that they're all in a box, there must be at least one box with more than one pigeon. They could all be crowding in box 1 if you wanted them to, but at least, there must be at least, like, you can space them out, and then somebody's got to double up. If you're telling me all the pigeons are in these 6 boxes. It's impossible otherwise, okay? It's very simple, but very useful. And we can prove this by contradiction very easily. It's like, okay, assume that assume as a contradiction, the opposite of the theorem, assume that every box has exactly 1 pigeon, or less than or equal to 1. For a contradiction, that means then number of pigeons is less than or equal to 1 times n equals n, but number of pigeons equals n+1, which is greater than n. Contradiction. QED. Okay, so it's a very simple thing. If you have n+1 things, you're trying to put them into n different boxes, well, you're going to overlap. And really this is talking about functions. It's like, okay, if you have functions going from this set to this set, and the domain is smaller, it's just saying that you are forced to double up somewhere. That's what it's really doing, okay? Maybe I should write that somewhere. Okay, domain and codomain sizes. Eee. That's the idea. So that's a pigeonhole principle, and let's do some cool stuff with it. So, examples. If you have a drawer of 3 different kinds of socks, and none of them are in pairs because you're a horrible person, then, in the worst case, you have to take out 4 socks until you can find a matching pair. So let's say you have 3 different kinds of socks in your drawer. You've got S1s, a bunch of those, S2s just laying about, and then S3s just laying about. Just a bunch of those. How many, in the worst case, do you have to take out of the drawer until you find a matching pair? Well, it's going to be 4, because you can take out an S1, an S2, and an S3, or of this in any order. And then the 4th one is required to be one of these other ones, okay? You have to wait until then. Like maybe it's an S1 now. and then you finally have a matching pair. Okay, you have to wait though, because you might be unlucky. And this is, we're talking about how unlucky could we be, okay? And we're using the pigeonhole principle deep down. Isn't that funny? An even more funny example is there are, and this is a fact, okay? We can't find these people, but it's a absolute fact. There are 3 non-bald people living in Fresno with the same number of hairs on their head. Can you believe that? It's hard to believe. It's just math, though. The number of hairs on someone's head is apparently less than or equal to 200,000. Okay, so you can have anywhere from 1 to 200,000 hairs on your head, all the options in between. And Fresno has a population of around 500,000. So even if, like, you spaced out as far as you could all the people who had 1 hair, and then the next person only had 2 hairs, and the next person only had 3 hairs, you tried to space them out as much as you could, you're still going to overlap a bunch of times, okay? Because 200,000 goes into 500,000 because 500,000 divided by 200,000 is greater than, strictly greater than 2. And so there's going to be an overlap in one of these bins at least 3 times. Are you following that? That is crazy. There's going to be an overlap because there's a remainder, and you get 2 in the end. Okay? That's the idea. And so really, you're using the ceiling function. It's 500,000 over 200,000 ceiling. Okay? It's going to be 2 point something, and so it's going to give you 3. That's the number we're looking for. There are, at a minimum, 3 people with the same number of hairs on their head. Okay? Living in Fresno right now. Crazy. Okay? 2 more examples, and then it's over to you, and then we'll get out of here. All right? So 5 cards, pick them from a deck. At least 2 must have the same suit. Again, pigeonhole principle. You have, what are they? Clubs, spades, hearts, and diamonds, right? And so here's like the first card, second card, third card, fourth card. Well, if you have 5 cards in the deck, and this is as spaced out as you can make them, you're forced to have one of the previous ones. Like here's like another heart or something. This one is forced to be one of these other ones, okay? It might be even better than this, like maybe they're all clubs or something. But in the worst case, I hope you can understand that, in the worst case, 5 cards, you're trying to space them out as much as you can to get as little overlap as possible. You just like run through them all, and then you are forced to overlap, okay, if you have 5 cards. If you have 4, then it's not a guarantee, okay? Another example, because this is just a fun topic for me, pick 10 arbitrary 2-digit numbers. Now this one's crazy. 10 arbitrary 2-digit numbers. I would like to ask the class for them, like, I don't know, 15, 21, 33, 87, pick 10 of these 2-digit numbers. There are 2 subsets of those numbers, we're not sure which ones they are, maybe it's like this one and this one, that have an equal sum, no matter which 10 2-digit numbers you pick. This is absolutely not making any sense at all, but I'm going to prove to you, using the pigeonhole principle, that this is true. Because the number of possible subsets of these numbers is 2 to the 10, right? That's the number of subsets. That is the idea. It's not size 2 subsets. It could be like a size 2 subset and a size 3 subset. It's just 2 different subsets that sum together to be the same, okay? So that's the number of subsets we have. And here are the set of possible sums that we could have out of these 10-digit numbers, right? We could pick anywhere from 0, 0, 10 of those. So that's the smallest number we could have a sum to. And then the largest number we could have a sum to is, okay, you just pick 99 10 times. And that's 99 times 10, which is 990. There are 991 elements of this set, 1,024 elements of this set. And so this one wins. There are more subsets than possible sums, so there has to be an overlap. Do you see that? It's greater. Strictly greater. It's insane. Unfortunately, we don't have time to code this up, but if you want to talk to me in office hours, you can probably convince me to do it there. Okay? This is crazy. Pick any random 2-digit numbers. You're going to find 2 subsets, at least, that have an equal sum. That's so crazy. Okay, so 3 examples. maybe I'll just pause the video, let you try them all, and then we'll come back and do them together quickly so we can get you out of here. Okay? So, first one. How many people must be selected to make sure that there are at least 20 who are born in the same month? And so again, think of this as spacing everybody out as much as possible. So you can pick the first 12 that are born in separate months, right? And then the second that you have the 13th person, they're forced to overlap. You got to do this so that you have 20 born in the same month, okay? And so the idea is, in the worst case, you have 19 overlaps. Like they're all overlapping 19 times. So there's 19 times 20 people. And then you add one more person, okay? So in the worst case, these overlap, times 12. 19 times 12. You can split up 19 times 12 groups of people into, okay, they're all sharing an equal amount of each month. That's the worst case you can do there. And then the second you add one more person, they're forced to spill over into the 20th group, okay? That is the idea. We're just trying to find a number such that n divided by 12, the ceiling, is greater than 20. Okay, that's what we're looking for. And so it just so happens to be, okay, n 19 times 12, or times 12 over 12, well, that's 19. That's less than 20. But, the ceiling of that. But when you do plus 1, it's 19 point something, 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 which is really 20 when you take the ceiling. That's the idea, okay? And so, sorry, it's greater than or equal to 20. That is the hope. That is what we're looking for. So, that is the answer there. And then, okay, another question. How many people in a group of 50 were born in July? And this one is a trick question. I'm sorry about that. I had to give it to you. You can't tell. There's no way of knowing, okay? There is no answer. Because this is a very specific month. When you get specific, your day can be ruined. You can just find a group of 50 people who are all born in January. You see that? You see how that's quite different to this one? It's just like same month, whatever it was. This one's exactly July. There is no answer to this question. Okay? It's not even a question. And then finally, let's talk about California. The population is 40 million-ish. So at least how many people have the same 3 initials? And let's just assume that everybody has either a middle name or like 3 names, like 2 last names, so that you have 3 initials still. And so the idea is, how many different initials can there be? It's 26 to the power of 3, right? These are the number of initials. And what we want to do is take this and divide 40 million by it, okay? Because this is all the ways that you could double up, like put everybody in the AAA bin, the AAB bin. As little as possible. What is the overlap we are going to see? Okay, at least how many people have the same 3 initials? 40 million over 26 to the third, the ceiling. Okay? That is the idea. So take this explanation, take the book's explanation, bring them together, and it should make plenty of sense. Okay? So that is the Pigeonhole Principle. It's a very fun topic for me, and hopefully you are now masters at counting. Please yell at me if you have any questions at all. But that's all I have for you. So I will see you later.